Very good. All right. Well, I hope you had a good lunch. And interestingly, we're having pasta after lunch. I didn't want you to chew on these and spoil the model. But everybody should have at their table at least one of the little trays filled with these, I call them I'm Peppy models. Just to answer the question, these are made of acini di pepe pasta. And that's where I got the name Peppy, because that's what the name is, so that's why I call it that. And also, I bought the various types of pasta in Denver, San Antonio, and Aiken, South Carolina. And so they're actually 3 different materials. Okay, they're very close. Some are smaller, some are a little bigger, and then there's one, and what I have, they're like a piece of spaghetti that's been cut in very short chunks with a hole in the middle. Okay, some of you may have those as well as I. So they're very close, but they're not exactly the same. Almost all, except I think for this one, are about 2,200 parts per million. Okay, I've designed them so that they're about that, and they will produce interesting results. That's less than the 10,000 we talked about is kind of the magic number of being a trace element. So we will get the various types of Poisson distributions that we saw earlier this morning. And that depends on the size of your sampling device. Now, we just gave this recently in Aiken we had a whole new batch of new hire young engineers. And one of the things I had to tell them was how to do it, because as I mentioned, you can goof it up, okay? And it doesn't goof it up that badly, but it does bias. Okay, so we'll talk about that. Everybody should have a tray with at least 4 different sizes of sampling devices, or teaspoon, tablespoons, whatever. The largest is a tablespoon, although I think these guys have about a 25,000 part per million, so about 2.5% model. So they're going to get different results than the rest of you. And the largest one, the tablespoon, will get a lot of sample. It'll get, hopefully, a lot of the little either red or green particles that are the contaminants, or I call them hits, that we are looking for. Now, you should also have several plates, okay? And these are very important. And while we're in the mechanics of it, you should also have, Tressa, did you put out the sampling forms, or are they in the manual? Tressa?
I'm sorry, I was talking.
Are the sampling, are the recording forms in the?
They're right here.
Okay.
We're doing it. I'll
Pass them out.
One thing we didn't do.
Okay.
Everybody?
Everybody gets one. Yep. Now, you may want to have 2 people go on the other side of the table so that you can all face the model and all reach it, because you'll need to be accessing the model. All right. So, again, this is based on my experience at Montana Tunnels Mine. Here's another picture. This is not the geologist, but it's one of the geologists. You can see they've done a lot of work out there, mining a big open pit. Oh, there we go. This is based on the idea that we have large particles. Here's a nugget of TNT, about a golf ball size, that we could have. Some of these are red, that kind of emulates the TNT, say from a washout facility. As I said, this is an example of windrow composting at Pueblo Chemical Depot. We'll do a case study on this. This is where I was worried about finding those potentially undegraded nuggets of TNT. Also, as I mentioned, we'll do a case study from Savannah River. These are high-level waste tanks and robotic crawlers. Very interesting site, doing radionuclide characterization. But today we're going to have, we don't know if these are gold nuggets, we don't know if they're TNT or bombs or whatever they are, but they're nuggets, or I call them hits, that we're looking for, some type of particle contamination. As I mentioned, the models have about 2,200 parts per million. And now that you have a recording form, I'm going to borrow one here. On the x-axis, it has the number of particles that you will scoop out, and I'll show you how to scoop in just a minute. And on the y-axis is the frequency. And what we're going to end up doing, and we'll show you here too, is make a histogram of your sampling results. And they'll look similar to those histograms that we saw in the Poisson distribution earlier this morning, where they're kind of spikes sticking up out of the x-axis there. Now there is one group, these fellows over here, that have a 50,000, I guess it's 50,000 part per million, about 5%. And their recording form is a little different, and I gave them smaller sampling devices. And we'll have them explain why after the exercise is over. Okay? They will be more than happy to tell you.
We don't have to count as many pieces.
Well, all right. I think you get the idea. Now, you should have lots of different sizes. Not everybody has a 1/8 teaspoon. If you don't worry. The one thing I would ask is that within a table group, that at least every spoon size is represented. Okay, so you may have, 2 of each type, but make sure at least 1 tablespoon, half tablespoon, teaspoon, blah blah blah, is somebody does that. And if you have duplicates, that's fine as long as you have a complete set. Okay, that's one of the major things I ask. I also request that you check the little box that says what size tablespoon you use. Okay, that'll be good. That keeps them straight, because sometimes I have our students or our young engineers record these. And the other thing is, when you fill in the box, fill it in fairly completely. Sometimes people put little dots, but I'm going to make you try and color it, because we're going to show some of these after we're done with the exercise, and it's easier for people in the back if you could see a solid block. So little logistics there. Okay, now the idea is this is a pile of some sort, and we take our sampling spoon, and if you want you can randomize it, but it really doesn't matter too much, and you dip it into the pasta and you pick up a spoon. Now I don't do this, okay? I dip it in, I take the whole thing, I make sure it's full. Last time I had it was an accountant, a bean counter, who turned out not to be very good at counting pasta. He come up with something like this, a partial tablespoon. Ruined the whole thing. But it did give me something to talk about at the end. So since we're all kind of, we're not accountants, at least I don't think we are. I don't hope I don't offend anybody. Get a big spoon. Heaping teaspoon, tablespoon, whatever you got, I want it heaping, okay?
And can you shake between each sample?
If you want, you can do this. In fact, some people find it quite therapeutic. So yes, it's not bad to randomize. I won't tell you that. I'll tell you something later about that. It's very interesting. So the idea is you take whatever device you've selected, heaping tablespoon, you take the little plate, and you pour it out, and you count the number of either red or green hits, particles, that are there. I got 0, and I have a half teaspoon. Okay? I then record on the form 0 in the first box. Okay? Then we do it again. Okay? Again I got 0. Okay? I would record another 0. And I'll show you how to do this, because there are 2 ways very smart people record. Okay? One is the way I do it as a statistician, which is in histogram form. The other is a very smart way of doing it in its time series. Okay? So I'll show you the difference. And if you find yourself doing a time series by accident, don't worry. Trust it's got extra forms. We can take those same data, push them down, no problem. You're okay. All right? You're just smarter than statisticians. So, where did I put my... Here we go. Okay. So basically, that's what it is. If you want to mix it in between, randomize it, I have no problem. If you don't, I actually don't have a problem with that either. When we do the beads, I make people randomize between. It gets noisy, but we don't have that problem. Here we go. A histogram, the first, okay. In a histogram, the first recording goes on the bottom line, whatever the result is, okay? Let's say it's a 22. Now, we actually don't have a form with a 22 because I changed the system. I'm sorry, let's say it's a 21. If the next one is also a 21, it goes on top, and you keep stacking them. You don't do it like this, where the first one is this, second, third, fourth, fifth one goes out here, eighth one goes out here, okay? This is the time series. We want to produce the histogram graph. If you find yourself with this, we just take these and squash them all down. No big deal, and no harm, no foul. We can recover the data. But
So every time you take a sample, you're writing in,
you're filling in a block.
fill it in a block.
Right.
For the number of hits there are in that sample.
In that sample. So
Stacking it on top of the previous one, if two in a row are the same number, you'd have 2 blocks on top of each other.
that's correct. And so for you guys, you know, you might have 10 hits. So you're going to be way out here on the x-axis. Some of you guys are going to be bored because you're going to have a lot of zeros, okay? If that happens, don't worry. We talked about that kind of earlier, about small sampling devices. This is the whole point of the exercise. So, again, let me make sure I don't miss anything. Okay, that's it. Take a sample. Well, what we usually do is wait until the people with a lot of zeros kind of max out, and then wait a couple minutes and let people get a few more samples, because these guys are going to... 30 times would be good. Yeah. Now, some of you won't get there to 30 because you're counting too many times. Right. All right.
I need another form.
Oh, sure.
And one
One size per sheet?
There you go.
one size per sheet.
One size of teaspoon per sheet.
Oh, one size.
Yeah. Always,
Pick your weapons, guys.
right. Always use the same size teaspoon. Okay? Okay. We are ready to move on. We have some great results. Oh, I got to see those. They're in here. We'll probably come to them. All right, let's see what we got. These are not in any order. We don't have time to really sort them, but we'll see what happens. Here is a 1/4 teaspoon. That's a fairly small sampling device. What do we get? A skewed, kind of a log normal distribution. Very typical. How many of you had 1/4 teaspoons? Is this about what you got? Something like that? Yeah, very common. Very common. Now, here's somebody who had a tablespoon. And this is interesting with a 2200 model. They were headed toward a normal distribution. Okay? They had a lot of counting to do, more than other people, because there was up to 18 samples. That was your low end. All right. And why did he have so many samples? How many of you with a tablespoon counted 18? You did. That's amazing. Okay? That's really interesting. He cheated because he had the 50,000 part per million. And so he was doing a lot of counting. He was up, his lowest was 5. Okay, the most was most frequent was 9, and then he had a lot of 12s and 15s. Oh, that's yours? That's interesting. Tell me who else worked at your table. Maybe I have a second high content model. So that's really interesting. We'll keep that one out. All right, here is a 1 teaspoon. It's trending toward normal. Not quite normal, as I told some people when we do the bead models, which are perfectly normal. Sometimes we get stuff like this. It's, you know, sort of lumpy in the middle, but not the perfect bell-shaped curve that you expect, and I tell you about in stat class, which happens with people's heights and weights and, you know, things like that. So now we have a half teaspoon. Interesting results. Kind of, sort of trending toward normal, but not as good as the teaspoon. This is a tablespoon. And this one's kind of headed toward normal. It's got a nice big spike roughly in the middle, but it's still got a little tail out there. Okay? So it's a better result. Here, oh, I know, this is from this table, or maybe it's from your table back there. Here we go between 15 and 30. That's yours. Okay. So, again, it's... Yes, that's a teaspoon. Oh, that's almost mean, isn't it?
Yeah.
That's why I warned you. They did a lot of counting. That's why he doesn't have too many samples. In fact, you did pretty well, I'd say, on that. Here is a half teaspoon, probably from your table also. Okay? Now, how many of you with a half teaspoon got this normal a distribution? And it's probably more geared towards zeros and ones. Yeah, I see heads nodding over there. Okay? And also you can see the whole thing is shifted to the right. Okay? This is why we like to have large sampling devices. Okay? And it helps when you have, I cheated because your model is more normal to begin with. But when we go to a large sampling device, we get something that's a lot more normal. Okay? So that looks good. Again, here's a 1 teaspoon, kind of sort of normal. But when you go to the tablespoon, that's what I call normal. That's good. So we won't go through all these. Let's see if there's anything very unusual that pops out here. You know, we get a lot of skewed stuff. Here's one that's kind of normal. Here's another big one. But a lot of these. A lot of you had these, didn't you? Okay. And you're all sampling from the exact same material. And so if you send in a field sample that has this mass to the lab, as I said, you know, if the guy at the lab takes a little bit off the top, you're rolling the dice. So you have to tell them how to sample and subsample when they get to the lab. So that's the lesson here. And it serves to illustrate the point that we saw earlier, that the physical size of the sampling device determines what kind of statistical distribution you get. Now, if you've done statistics, you know it's much easier to apply normal statistics because everything's symmetrical. And the equations work out much better. If you go into log normal, they get really messy. And we get all caught up talking about theory in our decisions and this and that. So, if it's all possible, we want to use the sampling theory tools to design in a proper field sampling volume and any subsampling volumes that may follow so that we keep that fundamental error low and that we can try and go for these normal distributions as much as possible. What we don't want is something that looks like this, and I know a lot of you had something that looked like that. Okay. So, hopefully that was a little bit new for you. I hope you never look at sampling quite the same way. We'll talk a little bit more about this in the next module. Let's see, I don't see anything that's... Whoever did this, my hat's off. You got a lot of samples. You're very speedy. Yep, here's one they only got 3, but they got 1. And there is variation. Sometimes this is a 1/4 teaspoon. Sometimes they got maybe double that. You never know. Sometimes the big one didn't come out as normal. I saw a couple of those. But that's the luck of the draw. As I said, with the perfectly normal B distributions, we get all manner of variation. Sometimes you hardly get the mean, and it's kind of split. Sometimes you get lumps on one tail or the other, or flat lines. This is random sampling. Even though the distribution in the box is perfectly normal, just luck of the draw. It's like if you flip a coin 10 times, there's actually a surprisingly large chance you'll get 10 in a row. Okay? I mean, I'm talking like 1 in, I don't know, 200, 1 in 2,000 or something like that. But to have a run of 5 or 6, not unusual. So you have to understand the material you're working with. And I thank you for your patience. I know it's hard to count, kind of frustrating sometimes, especially if you have the big tablespoons or the big model. But, and as I told somebody recently, I said, it's hard to believe that these are a scientific teaching device. These little pastas and tablespoons. But anyway, hopefully that sets the hook about the size of the sampling device being important. And that applies, you know, say if you have a large windrow and you're sticking a tri-ear in or whatever shovel or sampling device you're using, that's a small sampling device. And so the one lesson I'll say here is that here's one from a tablespoon, and it's approaching a normal distribution. How can you get a 1/8 teaspoon to look like this? Lots and lots of increments from the 1/8 teaspoon. You could fill up a tablespoon with 1/8 teaspoon increments to create a 1 tablespoon sample.
So, let me make sure I understand. You're not saying take 1,000 and count and record each of the 1,000.
Right.
Because that would just give you the skewed one that we saw, only more so.
Exactly. In fact, I will show you. Okay. I'll take the smallest one I have. This is a quarter. I dip, I fill. I dip, I fill. And I keep going until I fill it up. Okay? Each one of these dips is an increment. Okay? Now I'm taking them in the same place. I can vary it. But you could do this in a pile and say, now I have a sample. Okay? I pour it out. I have 2. Okay? So it took all those dips just to get 2 little particles. But now I have 1 sample. And now I'm going from the kind of the 0, 1 binary that we saw in the dots diagram up to starting to capture at least a few particles every single time. So this was not a sample. This was really an increment to create a sample. Okay? Yes?
Question. So I know that's a pile, but let's pretend that pile is not really so big. And I've got a spoon that I'm going to fill up into a bucket. I mean, where do I go around the pile and look at stuff like that? Like, just randomly?
Yeah.
And I keep it to the center and I can't mix?
Yeah, I would go with a random. You could go with a grid, but random is usually better. Now, with 200 feet, you might want to break it up. For instance, we did that with one of the case studies with the petroleum-contaminated soils. Because random values tend to cluster, and you'll see this in the case study. Sometimes we gridded this thing, and you'll get 3 or 4 right next to each other or in a cluster. Okay, well, if you just happen to get a goofy random number generator, you get everything on one side of the land farm and not on the other. So we broke it into 4 chunks. And within each chunk, we did like 10 random samples, or actually 15. So that you were guaranteed to have some kind of semblance of equal spatial distribution and still have randomness. Okay, that's a decision you make. I think I've got a slide or 2 on another area. It was around a schoolhouse in California. We just went random. And wherever they fell, that's where they fell. Okay?
Well, random, how do you, I mean, you have to not, like, I could go out and say, well, I'm doing a random, but go, oh, it's not one here, so I'll pick one here.
No. That's biasing.
Yeah.
You need to have some accountability on saying this is a selected location and making sure with GPS or taping off on a pile or whatever, you know, both from the length and the height okay, that you're taking it where it's supposed to go. Okay?
I was doing an agronomy sampling out in a pit of 120 acres, and we told people to go random, and they said, okay, we'll go over there, and then we'll go over there. And what they were doing subconsciously was selecting all the hilltops in the pivot where the soil's thinner. And it's because, okay, we'll walk over to that spot.
Right.
When we figured out what was happening, it had skewed all of our data.
You know, one of the DEQ people sent me a situation where there was a land farms in this state, and there were 2 sampling events. They claimed they were both random. And when I looked at the first one, I called my contact here and I said, they're not telling you the truth. I'm not a betting man, but if I were, I bet you $1 bill it was not random, because there were no clusters. And you'll see in our case study, I did a random. There's tons of clusters. I mean, you look in the pasta, you know, they group. You know, they're kind of wide apart, but they cluster. We saw all the, you know, the candies and carrots and stuff like that. Things cluster. So I knew immediately, not that it probably really mattered, but I could spot that it wasn't a random sampling from a mile away. Just because you get stuff right next to each other. And we'll do a little exercise here in a few minutes to kind of demonstrate that. The other thing, the last thing I'll mention, is in this model, somebody found this little elbow macaroni that's brown. We got cross-contamination from the factory, apparently.
I have a question about that, about the land farm and the call. I mean, isn't it more appropriate to say, instead of that they lied, that maybe they don't understand the concept of truly random, so they were biasing their samples, so they didn't necessarily lie about their sampling, they truly thought it was random, even though it wasn't with your base level of knowledge?
You know, it's, I don't know if I'd call it a lie, but maybe it is, but it probably didn't make any difference, because what they did was they spread them out. So there was kind of sort of an equal distribution over, which is not necessarily,
And they probably thought that was random.
and they probably had that as a definition of random.
Right.
And in the end,
So isn't it the regulator's responsibility to guide them and say, this is what we mean by random?
well, this is the kind of discussion I like to have up front in DQOs when you start that. I mean, in the end, it's probably the responsibility of the permitted party and/or their consultant to ask those questions. But, you know, to avoid that situation coming up, you know, after they've gone out and taken all those samples and they say, this isn't random, or we don't think it's random. It wasn't I'm not saying it was bad. I'm just saying I could tell you right now that with a high probability, I mean, if you threw darts at a grid, it would be almost impossible not to have some next to each other, or even hit the same grid cell a couple of times. And that happens in random number generation. Sometimes, I do it on my HP calculator, okay? Sometimes, not very often, I get the same number 2 times in a row. It happens. Numbers just cluster, because I do 1 to 100 generally. Okay, so, you know, every once in a while you get 255 or something.
So Jeff, I just want to make sure that I'm understanding. I think you're telling me that in the sampling plan up front, before any work is done, it's written what random sampling is. It's written down that, not just the word random sampling, this is how it's going to be achieved.
You could have a statement from the consultant or the party that's saying random sampling will be done via Excel spreadsheet or HP calculator or a random number table. I mean, there's lots of ways to do this, and it could specify that. If they want to break it up into sampling units, which we'll talk about, that's okay too. But everybody just needs to know, or if you want to say, we'll distribute them kind of judgmentally, randomly, and if you guys are okay with that and everyone else is, that's okay too. You know, random is more defensible because, you know, in something like this, you could say, well, there's no samples over here. Well, I'm looking at this. Guess what? There's no red ones either. But there's a whole bunch over here. And so if there's 2 in the red zone, so to speak, I'm probably going to find them. And if there's none in the barren zone, well, I wasn't going to find them anyway. So random is not necessarily, the clustering that goes with random is not necessarily bad. I think it's just our human nature to say, how can things that are clustered like that be legitimate and random when it doesn't seem to offer the spatial representation? And, you know, this is why incremental sampling gives us kind of one more arrow in the quiver. You could say, well, gosh, you know, teaspoons are cheap. Instead of doing 30 increments, let's do 50, 60, 100, okay? Or shovels in a pile or something like that. And then create bigger samples, okay? But, and we'll talk about this later. So there's lots more ways we can go about designing. But as we'll talk about here in the Once a Molecule lecture, the idea is that now we think about constructing a sample versus just taking one, okay? And you'll have to think these things through. You may even have to call me, say, you know, here's what we're thinking, does that work? Or call Trusted or somebody like that. But it's thought-provoking, isn't it?
It is, because, you know, if you're taking random samples and you hit a cluster like you mentioned, and then you submit that sampling event to the person that's regulating, and they don't understand the concept of clustering within random sampling, then you could be screwed.
Right, and that's, you know, if we ever do this again, hopefully we'll do the bead models. And we come out with distributions often that don't look really that normal.
Yeah.
But they are legitimate. And it's just, so to speak, the luck of the draw. Some of them are beautiful. Some of them,
Sometimes it's bad luck.
sometimes it's bad luck. But even a non-normal distribution could show very low or it could show very high. So, you know, that could be a function of bad luck in the random sampling. It could be a function of too small a sample support or not enough increments in a sample. So those are the things you want to think about before you send people out in the field and get that evidence that the regulator is going to say, well, there it is.
Because, I mean, in theory, somebody here with the 1/8 teaspoon sampler could have taken a scoop and got 20 little black beans.
Yes,
It could happen.
it could happen. It hasn't, but it could. There is a probability. You know, it's low.
Well, and something like, I'm the guy that it's going to happen too.
Yeah, I have this theory. It's like when I get on the airplane, I think that everybody pays a different price and everybody pays more than or less than I do. Yeah, I think that's how the airline works. It seems like I always pay the most for a ticket. So it can come back on you. And, you know, we'll talk about this, I think, in the next module here. These runs or clusters, even like flipping a coin, happen at a rate, you know, a predictable rate, in fact. And so doing experiments like this, we can start to understand the predictable rate. Now, some people do, and this is mostly in the mining industry where there's real money on the line. They'll go through lots of experiments, okay? They do what they call a 10x experiment. They'll take a whole bunch of small samples, analyze them, look at the variability, concentrations. Then they'll take a sample 5 or 10 times that size and see if the variability changes. Now, we know that as the volume goes up, the variance should go down. Because if you take that to the extreme and have the whole thing, there's no variability. Okay, volume variance relationship, they call it. If, however, the larger samples, those larger sample supports have more variability, that means your increment or your sample size was too small. That's how Petard figured out about those nuggets and said, you got to start mining your waste. You're throwing it away. So, you know, it probably cost them a few $1,000s, but I'm sure they, you know, were paid back in millions of dollars in recoverable ore. So the problem with that is, in the environment is we don't make any money on remediation practically no matter how it happens. So they have an economic driver that we don't. There's no incentive.
So you were talking about using the small sample to build, or incremental, create a bunch of incremental samples to create an actual sample size.
Right.
So applying that real world outside of the box, applying that to a large area, like Tessa was talking, like an acre or something. So then you fill up a bucket with your garden trowel, going randomly all over that acre. So now you have a bucket, and then you have to turn that back into sublots so that you can actually do something
Yes.
with it, is that right?
Yes.
So you're starting small, going big, and going back small again.
Right. Now, the other thing, too, that you have to factor in is that if you're taking a lot of increments and you're having very low concentrations, you may come back with a sample that's below detection limits. So you have to factor that in. But if you think you're going to get, say you're taking 30 increments, but you think everything's going to have concentrations, fine. But if you think half of those are going to be non-detects and the rest of them are going to be twice the detection limit, you're kind of on the edge of. But on the other hand, if your action level is 10 times the detection limit, you're probably going to show yourself okay. But every situation is going to be different. But you have to. There's a lot of new factors that you have to weigh. Typically we take 30 to say 50 or 60 increments, but it's good to have the capture of those particles. But if you're kind of on the borderline of detection and that's an issue, or other factors that might come in, you have to look at that too and think. You have to really think it through.
So are you analyzing those increments, or you're just
No.
putting all the increments together?
Right. You put all the increments to create one sample. And then once you get the sample, remember we did the nomograph up and down.
Right.
Okay. You take the subsample, crush it, subsample, crush it. However many times, and that's all based on that original group of increments that went in. Then that's subsampled, okay, or crushed and subsampled, and then over and over until you're done, and then you get the final lab sample.
Well, is that for assay work? Because in environmental, we're not crushing. So you can take a composite sample with a number of increments and put that together and mix it all together.
Right.
And then take a sample from that you submit to the lab, but we're not crushing from that point on.
Well, sometimes
So-
people do, like in the explosives arena.
Oh.
They do crush it. Now,
When they're looking for something particular, but like when you're doing site characterization or anything like that, you've already lost your volatiles at that point.
yeah, and
You're
you know,
compositing and-
incremental sample doesn't always work with volatiles for that very reason. But there are some, contaminants like explosives in particular where you may want to do that. However, there may be some scenarios where the risk assessor says, wait a minute, we're not grinding anything, because that can liberate bound up materials that will make it appear to be more hazardous, more toxic than it really is. So there's a lot of things you have to check. This is why we have that systematic DQO process. This is why we had one scenario where we brought on a risk assessor, okay, or a QA/QC person. This is why you want to get the team right, okay. These management consultants talk about companies, get the right people. That's the most important thing. Now we need to do the same thing. Who is the appropriate person on your team, okay? Because it does vary. Explosives or whatever you're doing varies from what Tressa and other people are doing. It's all very personal. It's what is going on at your site, how you're managing it, what the risk scenario is. There's lots of factors. So, anyways.
Well, that's what it sounds like the takeaway to me, is there isn't one specific
recipe or outline you can follow with all of this. Every site is unique and site specific, and you need to design those DQOs for that specific example. If you have volatiles, you're gonna have to do something different than if you're at the mine or if you're at the landfill. It's
Right.
very specific.
And that was really the concept, or one of them, behind DQOs.
Yeah.
Every site is different. You know, every PCB site is different, and every explosive site, and on and on. They're all different. Different scenarios, they have different objectives, they have different budget schedules, risk factors, everything. Politics, I mean, sometimes that's what enters into things. So yes, every DQO process is tailored to a scenario, which is not just technical and scientific.
So wouldn't you rather have the political fight before you actually have samples? Somebody spend a lot of money, and then you're arguing whether or not it's valid, have set your criteria beforehand.
I would rather do that. I would rather clear those issues off the table, the global issues, and say, let's make sure we're all headed in the right direction. Let's make sure we understand what a random sample is, how that random sample is collected, you know, how those are going to be used in terms of risk, how it affects the lab in terms of detection limits. You know, go down the list. This is why you don't just say, hey, Joe, write me some DQOs. Okay? He needs to check with people. You know, he needs to check with the finance guys, what's my budget, operations manager, schedule. Oh, by the way, you know, we're going to be messing around with trucks and samplers and shovels. Is that going to interrupt your operations? You know, I work a lot at DuPont, and they got real live operations going on with chemicals. And those project managers on site don't want you interfering with their operations. I don't blame them. So we have to work around that. So, you know, I think the DQO process is has its warts, and just like anything. But it tries to bring in various perspectives because, as you postulated, you really would rather have those issues settled before you get the data. And you may not like the data, or it may be unusable, or not satisfying. If you talk to Tressa, I know she has issues where data are coming in and they're not up to her standards, but the other side said, we think we're doing everything right. But they didn't talk up front. And so talking up front can oftentimes save a lot of grief on the back end. So, and I understand, you know, there's a complication. DEQ cannot be involved in the development, per se, of a sampling plan and a quality assurance plan. But they can say, here are the criteria by which we're going to judge them. Okay? That's what's the part of the DQO process. And, you know, we did, last time it was Waste Lagoon. And we have VSP, and you can run in there and in a few minutes figure out how many samples you need. But it isn't that simple, because the physical conditions at the site impact data quality. And so you have to have a checklist. Are there enough samples? VSP can do that. Are they quality samples? We talked about the Lamborghini versus the pickup. You know, was there ice out there? Was there a lot of wind? Was there this? And those could be mitigating factors that would make Tressa say, I understand what VSP is saying, but you're not meeting this body of evidence that is necessary to get the whole package. You know, for instance, if you got a letter in the mail from a sample you took in a lagoon or whatever, and said, lead, 25 parts per million, would you accept that? I wouldn't. I'm like, okay, where's the data package? You know, where's the QA? Where's the validation? You know, where's the instrument tune? Where's, you know, all the stuff that goes with that? It's just a number on a page, okay? VSP is a great tool, but in a sense, it's just a number on a page. There is a larger context, and we rarely make decisions in this world based just on one number or one factor. And so it's kind of a gauntlet that they have to go through. But Tressa has that on her website, on the DEQ website. They can go there, and the white paper is there, a version, earlier version. They can go there and say, okay, here are the criteria which will be considered and should be considered on both sides. And if you don't follow those criteria, or if you have questions, before you go out to the field to sample is the time to bring those up, have a quick meeting, series of meetings, whatever it takes, because if she or other DEQ people disagree and feel you did not follow the protocols that they were expecting, there's going to be hard feelings, because a lot of money and time has been invested, and everybody's going to think they're right. And those are difficult situations to mitigate. Yeah.
Suppose a third party enters in and accuses someone of environmental contamination, and then how do those play in the whole DEQ process? I mean, does that help like the validation?
The more kind of criteria that you can set out that demonstrate, this may not be the right word, but compliance, the better. Because then you can kind of check the boxes, and some of those boxes may be a little gray or graded. You know, you may be 70% versus 30% or 0, but I mean, nothing is ever perfect. And we all use our professional knowledge. But yes, I mean, if it is a litigation or a three-way party, you know, someone else caused, then you really, I would say you really need DQOs. Because inevitably, if it is really litigation, you know how that works. Every lawyer is out there to poke holes somewhere.
So like a site, I always tell people, and I don't know, I'm just have to suggest kind of validate, that your DQOs established that you did, you know, this data's good and it wasn't being,
If you have the DQOs to support it. Now, information could come to light after you sample. You may find a little surprise or something, and you may say, well, you know, if we knew now what we did when we did the DQOs, we would have done them a little differently. That could change the outcome. Or it could support your position completely and say, see, we did it right. So, I mean, there's always a risk. I mean, I have, in many cases, saved people millions of dollars on sampling. And one time a guy told me I saved him $29 million in 24 hours, okay? I'd love to work on percentage, but nobody will do that. I cannot guarantee I can save you any money, okay? I can tell you through VSP and other tools, we will minimize the amount you have to spend on sampling, you know, based on the science and technology, but I cannot guarantee I'll save you money because it gets you off the hook of a litigation, or because at Savannah River we were able to, you know, use incremental instead of discrete sampling and save 30, 40, $50 million. I can't guarantee those type of things. And, you know, you start off, as we talked about, with a conceptual model of the heterogeneity, or a conceptual site model as a whole. Well, everybody knows you go out in the field and you collect data. Sometimes you get surprises, and you have to readjust the conceptual site model because something changed. Groundwater flow pattern was different, a fault, you know, lens disappeared, or what, you know, who knows? Source wasn't doing the thing, whatever. And, you know, DQOs do not guarantee either a successful outcome. In fact, after the DQO process, there's a data quality assessment process, which says, okay, here's what we thought, we review the DQOs, here are the data, we review the data. Did they meet the DQOs we set up at whatever level of confidence? Hopefully they do. Sometimes they do not. And so you iterate back. Or you do a workaround, or you negotiate, or, I mean, but you may have to re-up the conceptual model and say, knowing what we do now, and we go back and do some focus sampling. Okay, not random, we do focus, because, oh heck, there was some kind of discontinuity there, and we focus around that, but it could be anything. So, you know, again, none of these things, you know, the incremental sampling, sampling theory, DQOs, none is a magic bullet. but they are definitely stacking the odds in your favor. And that, you know, this is what I'm doing with all these, where did I put them? Anyway, the histograms. I'm saying stack the odds in your favor. Design a field sample that's going to probably put out normal data, if you can. That'll help you, okay? That's legal, okay? So why not do it? And we'll see at Savannah River, for instance, one of the ways we saved them money was not just in schedule and time, but it was fewer analyses. So if you can cut out laboratory analyses, that's a sizable chunk of your budget, always. You know, we can a lot of times get away with 3 incremental samples. You know, 30, 100, sometimes samples are necessary to get certain contaminants kind of bound. So, yeah, it's, you know, it sounds like what could be easier than taking a sample? And now you might be thinking, gosh, what could be more dangerous than going out and taking a sample? Because there are a lot of ways you can goof it up. And as I said, in the early days, they learned the hard way that once you got the lab result back, like it or not, you had evidence. And evidence does not go away. So think before you go sampling. So I better move on. Okay, I'm sure I'm way behind. We'll catch up.
So just go to the next chapter?
Yes.